Welcome to the Stoa. The Stoa is a digital campfire where we cohere and dialogue about what matters most at the knife's edge of what's happening now.
Well, welcome to another session of the Dark Stoa. These are events that have a decent probability of blowing your mind and maybe inducing some existential horror. They tend to deal with heavier themes, and you can think of it as a negative visualization for what might be coming around the corner for humanity. Our speaker for this series is the infamous Pat Ryan, who some have called the most dangerous man on the internet. And he's got quite a treat in store for us tonight. So buckle up. There's going to be a talk. And so gather some questions as Pat gives his talk. And then there'll be a second part where we get to ask those questions to Pat. So without further ado, I'll hand it over to you, Pat.
Thank you again, Daniel. Howdy, folks. Thanks for coming back. Some of you weren't scared off by the CRISPR talk, and you made it for round 3, which is excellent. There was a great comment made about the CRISPR talk. For those of you who don't know, it was the discussion of applying hyper-consumer behaviors and marketing to CRISPR, resulting in some Tower of Babel moment for our brains, and it's just all going to go bad. One person saw the existential horror immediately and asked, well, can we reverse entropy? And I was floored by the ability to grasp the essence of the problem so quickly. And I said, well, you have to deal with time reversal. You have to deal with time symmetry. And the collective vote was that we should probably discuss what the two of us were talking about in full. And so this particular episode is designed to not get rid of the hope that time is reversible, but actually introduce the hope that we may have gotten our math wrong the entire time. And I'm going to preface this because I know that there are some in the audience who I am about to step in their domain and shit all over it in about as reckless of a manner as I can without the proper formalism and without the proper rigor. And I'm letting you know that's what I'm going to do. I'm going to ask you to give me a little bit of patience as I do this, because I'm not trying to go to the rigor. I'm actually trying to introduce a concept, and so I'm going to skip some dependencies for the sake of time. Like I'm going to go into the Riemann hypothesis, for example. And you know damn well you can't go into Riemann hypothesis without like 3 years of freaking linear algebra beforehand. And I'm not going to dedicate a whole episode to that. There's plenty of great YouTube resources for that kind of thing. So I'm going to skip through these concepts to get to the primary concept. So I beg of your forgiveness as I mangle your craft. But this will be interesting, I'm sure. And there's a little flaw that I've detected, and I'm curious if it's valid or not. So without any much more preparation, here we go. Let's see. Let me go ahead and share this. Present. Okay. All right. So entropy remains undefeated. You can't win. You can't break even. You can't even quit the game. That's entropy, folks. And it's sponsored by a little VPN company that I found that somehow found what I was saying interesting. It can hide behind quantum computers. It can't be quantumly broken. So if you're interested, go ahead and click on that and have fun. Okay, so let's get started. So we're going to get started with, I'm going to start as much to the beginning as I can without going full ancient Greece. So once upon a time, there was this guy named Rudolph II. He was the Holy Roman Emperor in the 1600s. He thought that Catholics and Protestants were pretty cool and the Jews were okay, but boy, that occultism was something else. So this guy named Michael Meyer was the court alchemist for Rudolph, and he wrote a whole bunch of stuff that was influential in terms of what we would consider Gnosticism and occult magic of the 1600s, specifically that time period, which is unique to that time period. And they got along pretty well, and he did all kinds of stuff, including looking like the guy who made John McAfee, which is an interesting feature. But he also wrote this thing called the Fraternity of the Rosy Cross. Rosy Cross, as you know, is a conspiracy-oriented secret society kind of thing. But it was derivative of the time. It was the 1600s. It was about 100 years into the printing press. And what the internet is doing to us now, the printing press was doing to people then. So anybody could write books. You can introduce yourself to all these ideas. You get these like little information cults all over the place, and people kind of fragment their information landscape aggressively. So the internet's the second time we're doing this, and books were the very first time. And these characters were part of that phase. And driving it this guy in particular was driving a good chunk of it. He found the whole thing fascinating. Matthias comes along. He says, yeah, Rudolph is, he's kind of a dick. I kind of want to get rid of him. So he gets rid of him. That's it. So because he knocked off his patron, Michael Meyer decides to run screaming and says, well, I'm done with this part. I'm going to now travel the rest of Europe and teach what I know about things. Of course, when one good knockdown king appears, another one appears as well. Ferdinand II decided to come along and says, hey, I like that throne. It'd be a shame if something happened to you. Matthias was basically saying, I'm just going to repeat whatever this cardinal says. That was the wrong answer. The right answer was fuck Protestants, in case you were wondering. He decided to go on a rampage and wipe out all kinds of Protestants, which unlocked the achievement called the 30 Years' War. This did not go well for most of Europe. This was a terrible, terrible time, and I made plenty of reference to it throughout all the podcasts that I've done. All of this then leads to the formation of Isaac Newton. Isaac Newton actually had a copy of the Fraternity of the Rosy Cross, and it was heavily annotated. See, the thing about Isaac Newton was that he was an archaeocryptographer before anything else. Before he was a mathematician, before anything else, he was mining the books of the Renaissance and ancient Rome and ancient societies in Europe to find secrets about reality. Just to put this in perspective, the Romans to the Europeans were about as equivalent as aliens to us. They were heavily organized. They had great technology. Their infrastructure was amazing. They spoke different languages. They had different religions, totally different cultures. And they just marched all over the barbarian Europeans at the time, especially the Germans. So when the Romans just up and disappear slowly because they just can't maintain their society anymore, they leave these roads and these ruins and these books and this technology everywhere. And you have a bunch of these forest cave people just running around saying, what is this alien debris all over the place? So there's actually a pretty serious demand for archaeocryptography, and Isaac Newton was definitely one of them. Okay, and he's the inventor of calculus, by the way. And these two things are very related, as we'll get into. So anyway, that's how calculus was born, in case you were wondering. So that's an important part, because calculus introduces a concept that we don't really deal with anymore. It's called the infinitesimal. I'll get into what that is as soon as my clicks start happening. Yeah. Okay. So let's start with differential calculus. Let's get these all out the way here. So this is an actual quote from, I believe this is from Newton's Waste Book, where he's writing down his ideas as he's coming along. And he says, what is x and y in one moment will be x plus infinitesimal and y plus infinitesimal in the next. What he was describing is the ratio of the velocities. So this infinitesimal bit, this is a hack. This is This is widely considered a hack. And it turns out that Leibniz relied on infinitesimals to a degree as well. When he was going, instead of trying to figure out motion, he was trying to figure out the area of curves. And he also relied on infinitesimals. So they both came to the same conclusion about this thing, and everybody saw the infinitesimal and was like, what the fuck is this thing? What do you mean an infinitesimal? So an infinitesimal is something that is infinitely close to zero without being zero. So like 0.000 repeating all the way down to like 1, right? So like 9 billion zeros to the right and then like a 1 at the end of it. So that's an infinitesimal. It is so tiny, it almost doesn't matter. And this was bolted on because of a problem because he's dealing with ratios. So by default, you're dealing with division. What happens if you divide by 0? Uh-oh. Well, the way out of that problem is to just bolt a fake-ass number onto it. Ta-da! You got around the problem. So that's basically what happened. And he was doing this to describe the tangent as it rides through different curvatures of motion. And the reason why he was focusing on tangents was because they had to use these mathematical constructs to represent motion. It's not like they had cameras and like rulers and like, I'm going to sit there and measure everything as I drop a ball. They couldn't do that. So they had to use the limited mathematical constructs they had at the time to represent motion in a semi-predictable manner. And so they would utilize tangents because that's what the limit of their math basically allowed them to do. So if you're wondering why all this stuff feels alien and doesn't make sense in the era of the computer, just kind of roll back to the 1600s and pretend that the only way to explore math was like by 5 different shapes. And that's all they had. So it makes a lot more sense when you kind of look at it that way. So again, as I described, if you're dealing with ratios and you're hitting 0, then you have some serious problems. But this, the very nature of the infinitesimal introduces 2 problems. One, you know you can't divide by 0, so you need the infinitesimal, but because the infinitesimal is not 0, you can't ignore it. Now, the whole way this equation happened was you go through the equation, build your ratios, and the way it was structured was at the end, you would then shrink the infinitesimal and then eliminate it from the result. So you get the actual number that you're looking for. But this, again, that seems like such a fucking hack. It's like, come on, man, you're taking me for a ride here, right? So that was not enough. That was his first pass, and that just wasn't it. And so he was forced to describe what he called was the fluxion. It was his way of trying to make sense of time-varying quantities. And it didn't work. So, like, yes, everyone's favorite degenerate gambler helped, but even with that help, it didn't work very well. In fact, this is another actual quote from Newton, where he cannot proceed with the explanations of fluxions. Now I have preferred to conceal it thus. Fucking gibberish Caesarean cipher. Actual quote, right? So not even he had like a firm grasp on it because the infinitesimal problem was bothering him too, and he had to be, like, obviously wasn't honest about it. He was trying to hide the fact that he just didn't know. And that's a missive to Leibniz. So they're both just like trying to figure this. The infinitesimals were problems, basically, is what I'm trying to convey to you, right? And we know what it is from a quantitative standpoint. We know that it's infinitely close to 0 without being 0, but what does that actually mean? What does that look like? Well, there was one critique to Newton at the time that was actually pretty damn good. And the more I look at it, the more on point I realize it is. And I don't think the guy actually intended this. His name was Brian George Berkeley. And he basically described infinitesimals as ghosts of departed quantities. Now that sounds like some pretty good prose. And the more I think about that phrase, the more I see why Newton had such a hard time with infinitesimals. And I'll be able to explain that in a later slide. And what he was trying to say is, he was saying that the church is one thing, logic and reason is another. So if you're going to bolt infinitesimals onto your supposedly rigorous logical mathematics, then you can't just bolt them on and we just take them by faith. Otherwise, it's no different than churches just spinning up miracles to keep consistency in their stories. So what you're saying is this infinitesimal is equivalent to a miracle, and thus it's equivalent to a ghost, and therefore we should just fucking get rid of them. And that was the critique that actually launched this and everything else. And this critique would last. It would stick for centuries. But there's something else in here that phrase, the ghosts part, is the most interesting part of that phrase. So I'm going to iterate toward that. Infinitesimals, as you can imagine, not only pissed off the church, but also pissed off the internet. You can see, you may have noticed this meme at some point a couple years back where 0.9999, which is an inverse of an infinitesimal, equals 1. You might have a memory of that sort of trick. So these things are just like problems across the board, these infinitesimals. You bring them into something and it just causes a mess everywhere. They're also, like I said, they were also holy wars. So there were so much so that there were some clerics in Rome that just straight banned them. Like you couldn't use them, like just get rid of them. Fuck you. They cause too many arguments. Then you have, again, Bishop Berkeley was the one who launched his very good attack in his work called The Analysis. And then you have the Lords of Autism, Cantor in particular, who is a walking human computer. There's no other way to describe him. They go on this holy crusade to eliminate infinitesimals from mathematics entirely. And then you have philosophical people like Russell and Carnap. They come in and they say, yeah, let's get rid of infinitesimals. We need, everything can be quantified. Everything's on the grid. It's all measurable. It's all computational based. Then you had a couple people who said, well, we kind of want to keep infinitesimals. They're useful even if we don't have an immediate use for them. And these guys were heavily mocked. These guys were attacked by every conceivable mathematician you can think of. And this lasted like this 1632. Like that's how long this fight has been going on, and it's holy wars. There's no other way to describe it. Eventually, Kurt Gödel comes along, and he basically says it is embarrassing that mathematics has abandoned infinitesimals. It's just outright embarrassing because at some point in the future, we're going to look back at these things and be like, what the fuck were we doing? Well, we know what the fuck we were doing. Bishop Berkeley said religion and logic cannot be using the same tactics because one's at war with the other. So he fragmented these things to say infinitesimals are identical to miracles, and so therefore we should ban them from mathematics. And in that little action, he doomed mathematical research for 300 years, utterly doomed it. And it took the efforts of Gödel, whose last name I can't pronounce because I'm not German. It took his efforts to say this is an atrocity. This is an embarrassment. All in the name of the post-30 war disaster. So let's get into the next part. So that's infinitesimals, right? Infinitesimals are these argument points, these sticky things. They introduce problems when you try to calculate for zero. They introduce additional problems like dividing by zero, for example. Why can't you even do that? You're always told you can't do that. It's like you get slapped, the fucking math police come and kick your ass. What happens? Well, you can't divide by zero because if you divide 10 by 0.1, you get 100, and then 0.01, 1,000. The closer you get to zero, the bigger your quotient. And that's why you can't divide by zero. So again, if we're starting dividing by 20, then 15, then, the closer we get infinitesimally close to zero, the quotient becomes infinite. So again, infinitesimals appear and they fuck everything up. So whenever infinitesimals sneak their way into a process, everybody just loses their shit. They're like, what is this? It's killing my ability to predict and my ability to quantify, right? Because we think of math as purely a quantitative thing. We don't think of it in terms of other aspects, although that's changing very recently because of computation. So is it infinity? Is anything divided by zero infinity because of the nature of infinitesimals? Well, the answer is no. And the reason the answer is no, because just because you get close to infinity by dividing by infinitesimals doesn't necessarily mean when you get to zero, you get infinity. So it's equivalent to infinity, but it's not infinity. I know that's a hair-splitting stupid, I'm sorry, but I call it unbounded. So it's infinity-like. It has all the properties of infinity, but it's not necessarily infinity. And to give you an example of what that is, an example would be in hyperreals, there is a concept called omega. So what you can do is you can take an infinite series of numbers, and you say all infinite series of numbers are equal according to these properties, but with omegas, you can bolt on these constructs afterwards to differentiate between infinities. So I'm of the opinion that this makes more sense in hyperreals than it does in our number systems. But again, I'm probably speaking gibberish and I apologize. What I'm saying is there's a math system where this concept of an infinity-like is feasible. So that's why I say it's equivalent to infinity without being infinity. Because just because you're using infinitesimals and the trend of behavior is that you're getting to infinity, it doesn't necessarily mean it will be when you get there. So that's why this is such a sticky problem. And so they just say, don't do it, right? So again, we're striking infinitesimals from math. The holy war continues. But what is it? But what we're actually describing here is a super task. So what's a super task? Everybody here is going to do a super task right now. The definition of a circle is a line that has infinite curvature, meaning a circle has infinite points on it. So because it has infinite points on it, how can I traverse a circle? There, I just did a super task. Look at that shit. Wow, I'm traversing a circle. Oh my God, look at that. I'm crossing infinite points with my finger, right? So there's a disconnect between infinity and actual work. So this bridge, this concept called a super task, it is how you complete a task that is made up of infinite actions. That's probably painful. Like, if it has infinite actions, how can you finish it? Well, that's why it's called a super task, because it's super. So again, if a task is made up of infinite actions, then it's made up of infinitesimal units, right? So it goes on forever. So again, now you're starting to see why this is so much of a problem. Like, how are we making sense of infinity when you can do a task made of infinite steps? So now the church has a problem with it, mathematicians have a problem with it, now you probably have a problem with it. So this is tough stuff. Okay, I'm going to do my best here. There are these things called prime numbers. I'm not going to get into them. I'm not going to get into what a zeta function is. I'm not going to get into Riemann. What I'm going to say is that we have a mechanism that allows us to predict where prime numbers appear. That's where I'm going to start this, and I'm just going to go from there. So just this is the methodology to detect where primes appear in a quantity line. That's all you need to know. So this is just, we're finding primes, right? But we can only apply this when we're dealing with if this value is greater than 1 and for its reflection and -1, which I'll be able to show that in a second. So let's say this is my formula. This is equivalent to what the Riemann zeta function is. I plug this into this, and then I represent all of this on a grid, like so, right? So if I say 2 plus I, it's going to go here. And then what the subsequent result of this is going to be this motion. All right, you follow me so far? So we're just going to look at that, right? So again, if I move my dot here, I get this motion. And if I move my dot here, I get this motion. So as long as these dots are beyond this line to the right, everything's going just fine. But what happens if I put my dot here, or worse, here? Well, it doesn't work. The equation becomes infinite. The answer becomes infinite. It becomes 1 plus 2 plus 3 plus 4 plus 5, all the way infinite. So you can't put this in here. So again, we're having problems with infinitesimals yet again. And this is the infinitesimal space right here. So as we approach 0, we start having problems. And this is showing up here as well. And by the way, if you solve this, there's $1 million for it. So if anybody wants to try a hand at this, there's $1 million in solving this problem. And what's most interesting is that with some finessing, there is a way to take those limitations that were in this slide here and say, wait a second, with a little bit of twisting work, I can use those limitations to predict where prime numbers are coming from. And here's roughly what the equation looks like. So here's what it visualizes as. This is that space we were talking about where you put the yellow dot and you get the pretty little curves and stuff like that. With something called analytical continuation, which I don't think I'm pronouncing that right, you can apply this to negative numbers too. What happens is if I start taking, wait a second, hey, get back here. Okay, if I take this equation, I put something here, it could be any number, and I follow these steps. If the something here results in 0, it will always show up on this line. Okay, so if I was to if my dot represented 0 here, my red dot where I'm at right now, and I decided to scroll to the left and it was changing the value that was in that S, you would see the following structure. So this is me at 0. And then as I'm increasing in time, t time right here, and I'm putting t into my equation, the output starts looking like a spiral, a corkscrew that continuously intersects with that half line over and over and over again. And it is this motion that allows us to figure out where prime numbers are, which is wild. Anyway, that's why this guy's a freaking genius. But this is purely in the infinitesimal space. So now we have a case where we're like, oh, okay, in this weird zone where we've seen 3 problems previously that the church had and that we had and that the internet had, we see a little bit of ray of hope. We're like, oh, there's an additional property about this space that is unique to all other spaces. And I'm going to come back to this in a moment. But this is basically, just to recap, I take that function and I apply, I continuously add the value that I'm putting in the function, and I get this motion of behavior. And this motion of behavior is indicative of a prime number, which is a key part of encryption and all kinds of shit. So that was a weird thing that was found. And this is confirmed up to 1 trillion of these loops. So we've been able to figure out, we can take these loops from here to 1 trillion, and we can find them, and we can predict up to 1 trillion prime numbers based on this structure alone. But we're still not confident enough to say that this is a proof and it's true in all cases. We're still not quite there yet. I don't think we'll ever get there either. But is this a super task? That I don't know. That is the outstanding question, I think. Because if this is a super task where you're taking an infinite number, where you're taking an action and resolving something that has an infinite number of operations, it is made up of infinitesimally more operations, then isn't this a super task? And if the answer is yes, then we might have an answer to this. And if the answer is no, then we got to figure out why. I'm going to double back. This is fucking complicated. And I don't blame you if I lost you on this, but I'm going to jump back. I'm going to make this more entertaining. This is like the hard stuff. This is the only hard stuff. So let's get into the fun stuff. Let's get back. Okay. So this is called the Minkowski hypersurface of the present. And this is supposed to be the fun stuff. My apologies, right? So what this means is you are here at all times. Your eyeballs, your life is here at this dot, and it never leaves this dot. So the future happens to you, and then it becomes the past. And however the future modifies you, let's say you turn your head, it will then rotate that cone. Or if you move somewhere else in the hypersurface, this whole thing being the hypersurface, it will rotate that cone and move where the cone is. So this is how most of calculations about how time affects people and observers, this is the model that's used for almost all of it. The idea is that the now, the future is some infinite thing, the past is some infinite thing, and the now, well, what is the now? Is it 0? Is it 0 time? No, it's not 0 time. It's an infinitesimal. How can I say that? How can I say that now is an infinitesimal? Because every conceivable metric of implied linear time contains an infinite number of these infinitesimal slices. How do I know that? Because I can divide time by 2 forever. I can get to the infinitesimal space when I divide time. I can say that, you can say that a second's made of 1,000 milliseconds. Okay, well, how many nanoseconds is that? How many picoseconds is that? You play the game all the way down. At some point, it is an infinite number of slices. And so what this model is proposing is that we are moving through these slices and transitioning through these slices at all the times. So every second is actually a super task. You are completing an infinite number of actions every second. And that's what this model relies on. So now we're starting to see that, oh, infinitesimals actually have an impact. That's actually time. And now is the infinitesimal. And there are infinite numbers of them per second. And this is what we've been using this entire time to make all of our cosmological and quantum projections. But as you can imagine, there might be some problems here. So let's explore. Well, first, let me make one more posit here. Mathematics has been trending anthropomorphically towards the idea of treating time as an infinitesimal slice. And the reason we've been doing it is because we can't stop seeing causality. We see it in everything we do. We can't actually stop ourselves from, we can't suspend our disbelief from connecting an action to another action. If I'm hungry, I go eat, that's causality. If I want to be somewhere, I'm going to walk somewhere, that's causality. So we have this linear perception of cause and effect, and the way we justify that in math is by treating now as an infinitesimal. Meanwhile, in everywhere else in mathematics, infinitesimals are effectively banned. So we have a model problem here, and I'll explain why this is a challenge. And this is exactly the example that I'm talking about, where physicists are just straight up inventing and assuming stuff. Specifically, the symmetry part. This is where all the trouble's starting, that I'm describing at least. So now I'm going to go back to Zeno, and we're going to say each one of these slices of now, the infinitesimal of now, I'm just going to call it a time slice. As these time slices accumulate over time, the ball raises. Okay? So we are representing motions one slice at a time, one infinitesimal at a time. But unfortunately, it's Greece. They don't have statistical correlation. They have no way of relating these time slices together, so they say that motion is impossible. At least Zeno did. Of course, Euclid came along and says, but I have legs though, so of course motion's possible, right? So this is the heart of the problem right here. We have never resolved this problem. We have come up with band-aids and tricks and fuck Zeno and then fuck Euclid and I don't care, and we've just extended upon this argument because we are obsessed with the idea of time being this linear construct because, well, Euclid decided we have legs and that was the end of the argument. It stays this way for a while. Then it gets to Newton, again, who is now coming with the ratio of velocity over time. It means he can predict future motion. He was out there trying to solve the motion of celestial bodies, planets. And as a result, he used ratio of velocity to come up with this. He wasn't just predicting the time slice of now, he was stitching together these time slices, these infinitesimals, into a prediction of where the infinitesimals would end up. Now, the problem here is that if you do that, not only do you don't just end up with future projections of where the time slices are going, but if you pump a negative number into your equations, you're implicitly going backwards in time too. So anything that tries to predict the outcome of infinitesimals always ends up in time symmetry. And Newton saw that, and that's why he was able to conclude, at least thought, that time was absolute. There's an absolute ticking of the clock whatever the infinitesimal is, and it's always happening. And for a long time, this was how people perceive time. The Clockwork Empire of Britain, for example, is all derivative of this work, really running with it. But this, again, it's still stitching together to time, and the artifact of that stitching is that you can see the future, but there's no way in which by modeling the future, you are also automatically modeling the past. And so what you're doing is you're creating this incorrect construct of time symmetry, and you're allowing it in your mental space and you're allowing it in your calculations. And so it kind of implies that time is reversible. And so you get these weird suggestions in your head, and then you're like, well, I don't know what's going on here. Well, then Einstein comes along and he's like, well, that's not true. There's some experiments I can come up with to show you that it's not true. And the way the way that Einstein looked at it, he said that all events were happening at the same time. There was no past or present or future or anything. It was all happening at all the time. It just depended where you stood to see it. So an example of that would be like looking at a star. You're not looking at the star right now. You're looking at the light from it that happened about 1 million years ago, 1 billion years ago. So if you stand somewhere else, you're going to see that light at a very different perspective, at a very different time. And if you're moving at the speed of light, then it's going to change how you look at all this entirely. So your velocity as you're moving through this space determines what you see. So you can't make a statement about time being absolute or being able to predict how events move through time or how they correlate The only thing you can say with confidence, or at least as a byproduct of this approach, is by saying that all events are happening all the time. Of course, this leads directly into Heisenberg, who comes up with a much more axiomatic observation and says, well, let's just look at these time slices. Let's look at these infinitesimals and say, I just have a snapshot of it. I can't tell you anything about where it's going. I know where this thing is right now at this infinitesimal. I don't know where it's going to go next. So he basically found a way to reinvent the infinitesimal argument by putting infinitesimals in the infinitesimals. And all of these, no matter how you cut this, it all leads to the same thing, the illusion that time is symmetrical. Now, whether the mathematician keeps the discipline involved and says, well, I'm not going to let that implication influence me or not. Sure, okay, individual discipline aside, but all of the models allow for a reversal of time. So this is one of those weird byproducts. And this is entirely because of the infinitesimal representation of time that we've been doing, because of that hyper surface present of now, where the future happens to us and the past goes away, and we're just sitting at this little plane. So how do you reconcile this? Well, first, you have to reconcile it because time isn't symmetrical. Time is asymmetrical, meaning when a thing happens, it doesn't roll back in time. And we have 5 examples of this. We have at the subjective level, our actions and decisions affect the future, but not the past. We can all experimentally prove that. At the electromagnetic level, we send signals to the future, but not to the past. If we could send futures to the past, then we'd all be rich because we'd hack the stock market. So there you go, right? That's out. Thermodynamic isolation, low entropy when it comes to things heating and forming organization. Things tend to get disorganized as time goes on, and you can't put that back in the box. So we see time asymmetry there too. Cosmological, the universe was small and hot, and it's getting large and cold. It's turning into a real bad marriage, And so that's more evidence of time asymmetry. And then the CP violation is some quantum physics nature saying, here's reasons why there's more matter than not matter. So we have 5 examples that are pretty hard to disprove about time's asymmetry, meaning time goes in one direction but not the other. It goes positive, but it does not go negative. So when our math structure tells us that time is symmetrical and we can deal with it symmetrically, this is a byproduct of dealing with time as an infinitesimal without coming to grips about infinitesimals. So we're making some pretty big mistakes here. And because it's an infinitesimal, we just write it off. It's like, it's only like 0.00001. We just drop it. We're still shrinking the infinitesimal, just like Newton did. We've just come up with these complicated mathematical constructs to explain why it's okay to shrink it without actually addressing the nature of the infinitesimal itself. It's probably the most fundamental time arrow. So time arrow meaning direction of time, as I was describing. And then we have H theorem, which is Boltzmann. So H theorem means gas atoms trend towards normalized speed distribution, meaning if I have a box, right this, it's a box, and I fill it up with gas atoms and they bounce around each other like billiard balls all day long, eventually they're just going to cool down. And so they're going to reach a normal distribution of speed between them instead of being hot all the time, right? So this is where things get clever. And if you've been following my argument, what I'm about to say next is going to get me thrown off of a building. I'm going to do my best. So no, fuck it. First, I'm going to do the visualization, then I'm going to say it. Let me get the visualization. Let me get you a point of reference here. So this is Minecraft. I don't know, just a box, right? So this is your life in 2019. We do one orbit, swing around the sun. This is your life in 2020. This is entropy. This is things that are organized becoming disorganized. And all you need is time to do this. Why is that the case? Is there something wrong with the blocks? No, there's nothing wrong with the blocks. The blocks are fine. It's equilibrium, meaning this thing is stable in an unstable environment. And as time goes on, the unstable environment wins. How can that be? Well, this thing's going to bounce into that, and that's going to bounce into that, and that's going to then vibrate this, and that's going to bounce into that. Before you know it, you have an equilibrium of velocity between all the elements here. Another way of looking at entropy is to say that it is the process by which indivisibles are reformed. Meaning everything breaks down to its one state that cannot be exceeded. Okay, so when I talk about H theorem and the cleverness of what that white paper said, we have to look at taking our infinitesimal time slots of this process of chaosing. We're slowly getting towards chaos over time in each one of these time slices. Our math tells us that this is reversible because our time slices are reversible, according to mathematical constructs. Nature says, you're fucking stupid. That's not possible. Everything's asymmetric. So this is the heart of the argument when it comes down to it. This is what the beef is all about. And because time slices are infinitesimals, we're still at Xenoverse Euclid. We haven't actually left it. So as a result, because that remains unresolved, entropy remains undefeated. You can't reverse entropy because we're treating time as infinitesimal slices. It has nothing to do with the system or the physics or anything. You can find entropy scale invariant. You'll find it everywhere. You'll find it in information. You'll find it in chemistry, atoms. You'll find it everywhere. At planets, life itself. So it's not the composition that entropy is commanding that's the problem. It's the way we represent time as infinitesimals without addressing what an infinitesimal is. So this is the clever argument I saw when the person asked me, can we reverse entropy? The answer is no, with a caveat. And here's the caveat. This is going to sound so fucking bizarre. If my projection of entropy is wrong, if I analyze these time slices and I'm incorrect about the chaos distribution, or whatever or the distribution of whatever it is I'm measuring, whether it's velocity or temperature or whatever dimension. If I'm wrong about that, then the wrongness is equally equivalent to time reversal. And here's why. If I project that this is going to form a brick over time, then I can't tell the difference between me being wrong and if actual time reversal took place. It's indistinguishable. And that is entirely a byproduct of this. And that's entirely a byproduct of this. So if we continue to treat time like infinitesimals, then error rates and projection of entropy are no different than time reversal. And that's why this is such a big problem. And somewhere a mathematician is probably having an aneurysm about that. And I'm sorry in advance. So, if we're going to deal with time as infinitesimals, then we have to talk about dealing with time as a supertask, which means anything you're using to measure action, to go through your hypersurface of the now. Anything that crosses that boundary is engaging in a supertask of infinitesimals, and we do not have the mathematics to represent that, which is why we end up in the problem where we can't tell our error rates from time reversal and why they're equivalent. So this leads us to all kinds of unresolved questions. Is it a supertask of infinitesimals resolving the hints of prime distribution found in the Riemann zeta function? Which, if it is, then holy shit, that changes everything. Do hyperreals interfere with the critical zone? If you start plugging hyperreal numbers in, which account for infinitesimals, and you put them in the Riemann zeta function, do you get the craziness that I'm talking about? Is nature's asymmetrical handling of time reflective of underlying cryptographic processes? Newton was an archaeocryptographer. In cryptography, there are certain types of cryptography that are unidirectional. There's an asymmetry to hashes, to MD5s and SHA-512s. So is time intrinsically cryptographic? Can we even come up with a mathematical system where time is asymmetrical permanently? And does it have cryptographic properties? Was the altist of Britain right all along? Y'all going to buy some VPN service? What do you want? That's all I got. And I'm sure that was pretty heady stuff. If you don't have a serious background in math, I do apologize. But please ask questions, and I'll walk you through it as best I can.
Wow. Well, thank you so much for that, Pat. All right, everyone throw your questions into the chat, and I can share. I'll use my discernment to pick which ones we should share, but I'll get a couple started. So in the beginning of the presentation, you referenced how Newton was actually working on a different project before he got into calculus, and you said how that's going to be relevant towards the end. I think I may have missed that. Can you spell that out a little further?
Yeah, he was an archaeocryptographer. So he was obsessed with trying to break what he perceived as cryptography everywhere. Basically, he was a conspiracy theorist. It's the easiest way to put it. So he was trying to crack encryption wherever he saw it, whether it was stego, whether it was hard encrypted or soft encrypted. And if what he was describing as an infinitesimal, as a byproduct of time, which he did in his equations. He said you had to put infinitesimals in there initially. The world made fun of him for that, but he wasn't wrong. You had to put the infinitesimals in there to get it started, to start that seed. What I'm proposing is that infinitesimal is a byproduct of a cryptographic asymmetrical process. So it makes sense why a cryptographer, a person who's coming from a cryptographic background would append that in there as an exception, because when you're dealing with cryptography, you are driven by exceptions more often than not. And so I think that's the relationship, which I probably didn't spell out so well.
Follow-up question is emerging. What implications does this framing have on the simulation hypothesis?
All of the simulation hypothesis needs to explain how time runs through it in order for it to be examined and tested. So if I was to say the simulation is whatever thing I want to throw in the air and say that's a simulation, I need to answer, is time relative, local? Is it calculated? Is it cryptographic? What are the properties of time itself? Is it a line? Is it a quantity? We've been treating time like a quantity for a very long time. Only recently, we're starting to look at time as a set of ordinals. But that's not the only possibilities. Time can be a living function, and we haven't even gotten quite there yet. So it's in order to figure out what your simulation's clock is, you got to start poking and prodding what the clock isn't, and then you can get down to it. And so what I'm proposing is that if infinitesimals are a byproduct of how all of our maths are dealing with time, then perhaps we can test to see if there is a simulation doing the same thing.
I guess one final question for me. I don't know if I fully appreciated the implications of mathematicians using models of symmetrical time if they're just kind of assuming, in practice, using discipline to not assume you can go backwards in time. What are the implications that are still bleeding into all the other downstream effects of using that as a model?
God, you get all kinds of dumb cultural artifacts. You get shit like the multiverse. So, guys, come on, give me a break. You start getting these weird constructs to represent stuff because, you get these regret wishes where, I wish I could go back in time, and you then point to a math and you say that's it. And maybe that's good for recruiting mathematicians, right? So there is some function to that when they're kids, whatever. But it is all derivative of basically making fun of Newton. That's what it boils down to. He said your infinitesimals are garbage, and he may have been describing the nature of time itself, and people just weren't fucking ready for it.
Cool. I'm going to start picking questions from the chat. Peter Wang, would you like to ask your question?
Yes. Hi, Pat. So very interesting exposition here. In all of this, I think there's still a metaphysical frame that time is this thing that can be sliced. I guess this is sort of your point, right? That we can treat as an infinitesimal. And I think Forrest and I myself sort of came to this kind of in a different way, but so it's quite a revelation to talk to Forrest Landry the first time about this. But this idea that, and I come to this as a physicist, right? So our assumption, our metaphysical assumption that that we're just okay with Zeno's paradox, right? We really haven't broken out of Zeno's problem. We sort of elide this as a super task and say, well, you know, don't worry about it. But my comment earlier about you've really not talked about the concept of energy at all, right?
Mm-hmm.
Because even when you talk about Newton and you look at the tangents and the differentials and all these things, it's a kinematic, it's a description of the thing. But really, I think the idea that, you know, we've basically said, let me try to say this in English, ask my question, ask an actual fucking question. The question is, what do you think of this, of this view that if there is something non-Zeno to time, now we try to pin time down on the same static cutting board that we put everything else, static in physical space, we thin slice it infinitesimally, and here it is, and now we're kind of screwed because we can't tell if we're going one way or the other way in time. What if we say, you know, fuck it, that's actually bullshit. There is a thing of time that does move forward, obviously, and is irreversible. What we've just simply done with the current metaphysics is we've squished all that dynamism into something we call energy, potential or kinetic. It's energy. So if you actually go and say, you know, time is not infinitely sliceable, it's thick. And the thickness of it is actually energy. Now we have a completely new metaphysical frame for a new kind of physics that says, no, you cannot just do simple decomposition into static objects with some bullshit thing you call potential energy that's infinitely divisible, right? Anyway, you see where I'm going. So what do you think about that?
I see exactly where you're going, and I didn't want to go there. And the reason I didn't want to go there is because it leads to a very uncomfortable conclusion. And I think I'm going to have to share it. I said I wouldn't to Daniel before I did this. And I think because you're there, I have to. The more I look at this, and I'm already batshit insane enough, and I'm going to take a exponential step into greater batshit insanity by saying this. The more I'm looking at time, and the reason I didn't go into energy is because I wanted to focus primarily on the infinitesimal nature of time itself and how we're treating it, and the problems of infinitesimals and what that means to entropy. Because if you can't tell your difference between an error rate and going backwards in time, then there we've hit a problem. So the way around that was to start dealing with what's called non-standard analysis. And I'm going to lose a lot of you. I'm sorry. I got to answer Peter. I apologize. Non-standard analysis deals with model theory, and it deals with things called hyperreals and hypercomplexes, which is a way of saying it found a way to put infinitesimals in the number line, in a number line. So now you can pack them in your number line, and you can make sense of them using a notation. And then you can start formulating. There's a convoluted way of applying arithmetic to those hyperreals, so you get the convertibility between normal number systems and that. But unfortunately, it alludes to the very uncomfortable concept of what you're calling energy. It's starting to look like numbers are alive. And that's where I lose everybody by saying that. So you're calling it energy. But in mathematics, in hyperreal land, it's not that it's a number on a line. It's not that it's a quantity or an ordinality. It's that the number is continuously reasserting itself over time. And that's how they're able to do hyperreals.
No, that actually makes total sense. Right? This is very much in line with Wolfram's sort of. It also kind of gets to the heart of why Wolfram is so impressed with his work on iterated agents. Right? It's like anytime you apply discretization to a thing that is fundamentally alive and constantly dynamic, you're going to end up with magical things that fall out in the residue, right? Because you've squished all of the dynamism out of it, including emergent things. Okay, interesting.
Yeah, and so so the hyperreal, basically, long story short, the time is implied and part of every number of the line. And that's where it's like, wait a second. With time isn't this like thing that we bolt on or measure against. It's actually implicit into the number. That's, like I said, that's why I say when I say numbers are alive, I'm talking about that particular aspect of it, which is like a 20-year talk after this one. So that's a great question. Thank you for bringing it up.
Thanks for the answer.
Yeah.
All right, Alexander Lee, do you want to ask your question?
Sure. So, well, in light of the last conversation, now I'm just kind of thinking about that. But it seems like there's a way to sort of map numbers and functions together. So I was wondering if you care to comment on the intersection between information entropy and thermodynamic entropy, especially with Schrodinger's negentropy, and maybe to see, well, whatever, I'll stop there.
That's a big one. No, please continue. It might help me out.
Okay, well, so rather than talking about entropy as you can see entropy sort of as different. So you have microstates and you have macrostates. And so the point at which you have a gradient or you have some sort of difference is when the microstates are readable in some configuration compared to the macrostate. So you can sort of see the infinitesimal, you can see quaternions, you can sort of see complex numbers as different dimensions of storing functional maneuvers within the real number line. So you can sort of see functions and numbers like interrelate in that way. And so you could sort of also then come to the conclusion of seeing thermodynamic entropy as a specific class of information entropy. And that then becomes really a way of understanding entropy as a function of measurement.
You're getting into Planck time.
So yeah, so then I was just wondering, do you think time is an artifact of how we process information and how we measure things? Because at no point is there a true zero. Like with Dede-Deakin's cut, you can sort of put zero at any particular position. So each point sort of then can sort of branch out and become, you know, a logarithmic root, for example, which is why numbers on the Riemann zeta function can have some predictability as to what's not prime, because, you know, 2n and 2n plus 1 and 2n plus 3.
Okay, so first I want to deal with the one statement where information entropy is a subset of classic entropy or thermodynamic entropy. The bridge is tougher than I think there, because the most obvious bridge is going to be Maxwell's demon. That's probably the most obvious bridge how you can get from chemical entropy to information entropy. Maxwell's demon is probably the bridge for that. And for those who don't know Maxwell's demon, it's the ability to basically break the balance of a system to get more energy than you thought possible. That's a very simplified way of putting it. But there are ways to do it in an information space, but it's still energetically expensive. So it's still, the question's kind of out whether you can do that or not. Because information entropy is measuring surprisal versus equilibrium, I think it's important to say, is surprisal itself an equilibrium? Is the question you probably want to start with. Excuse me, because the idea of information entropy, the bit, the flipping of the coin, the yes or no,
Sure.
It's a unit of surprisal, because you don't know what the thing's going to do. So a lot of information entropy is derivative of that construct. The bridge is a bit of a challenge. I haven't done a lot of effort on that, but I know that Hawking had done some effort on that regarding black hole entropy or black hole thermodynamics. And that's where the bridge he found was the idea that information is encoded in the black hole, and therefore you can use that functional process to then make the bridge to traditional thermodynamics.
Right.
So is it a class? Is it a class?
I think maybe are you familiar with Edward Schrodinger's book, What is Life?
I'm not.
So I think you need sort of negentropy as the understanding of, so you can sort of see negentropy as his explanation for why things are alive. And so you have the structure of matter that can be configured in such a way as to limit degrees of freedom of energy. Mm-hmm. And that processing, that direction of matter creates a constriction that is available for work.
I see.
And so that's his concept of negentropy. So that's how he explains life. So you can sort of see the pulses of a submarine underwater as sort of like it's the way it processes energy in a rhythmic way that is predictable, maybe.
Sure. The regarding how all this affects time.
Yeah. So like so with information entropy, you need a reader. Like you need something that is able to sort of read the difference.
Mm-hmm.
And so you have to have some basis for that reading. So that basis then sort of becomes zero. So with entropy, you know, things tend towards the middle.
Have you seen a scenario where information entropy is reversible? Is there a time asymmetry there too?
Yeah, I don't think that's really possible. I think that's because we can't really, because negative numbers are sort of imaginary. They're sort of just a projection.
Mm-hmm.
So to sort of get to that, we sort of have to start at a different basis, maybe. So each basis that we start at is sort of like what we consider to be like a container for the microstate. And so it becomes statistical, right? I mean, it's sort
Right.
of the conjecture that, Nicholas Taylor was saying about the stock market. Like it is something that can be predicted through probability, but it, you know, you just have too much information. Like how long of a stock market run do you need in order for it to start repeating? Is it like 10,000 years or whatever? And then you have Elichi, I don't know how to say his name, but he's saying no, it's actually a different sort of ontology. It's a different kind of metaphysics. So when you put it in a container of probability, you sort of constrain like how you can understand what's actually happening. And in order for you to predict the stock market, you have to sort of consider the relationships from the present and not use the past to predict the future.
So there's one scenario, there's one thought experiment that comes to mind about this, because when you're talking information entropy, everything's discrete. The infinitesimals emerge as a result of statistics in that type of space. They're not intrinsic, it's not a mapping problem until you start getting to high clock rates. So for example, as our clock rate becomes infinitesimal, you have, imagine a flash light bulb, right? So over T1, it's on, and then for 0.1, it's off, and then for 0.01, it's on, and for 0.001, it's off. So as we get closer to zero, the light bulb is flashing. It's as if it's on and off at the same time, when depending upon what resolution you're looking at. If you're way off, it looks like it's always on. But there, for example, there's one technology that does that. It's able to transfer binary technology through differential shades of amplitude of its light. So the lights in your house actually become Wi-Fi transmitters by using that technique. So the question is resolution of your clock. Mm-hmm. And that's where you start to get the infinitesimal problem all over again. So even in information entropy, you can still get them. And it's still bound to time.
Yeah, I guess I don't quite see the relationship of the infinitesimal to time. It's kind of, seems like I mean, there's definitely time in entropy. And in entropy, you sort of you need the microstates sort of to be in a configuration that's not readable. And so I can see the connection there with entropy, always with infinitesimals as being those particular microstates.
Yeah, you're dealing with discrete time when you're talking about information entropy. And so what I'm saying is it's not the discreteness of the time that matters, it's the resolution of the observer.
You know, that's interesting because it connects to Elaine Beddoes' critique that, you know, limit cardinals are a different kind of ontology. That when you jump from real numbers to limit cardinals or cardinal numbers, or you go the other direction towards infinitesimals and get smaller. So it's like a different dimension of interaction, and the logic that exists at each level is different. And so the formation of the new logic that appears is what he calls the event.
Interesting. What's that called? I'm going to take that one. That's a good one.
Yeah, it's his book, Being in Time, or was it Time and the Event? Hold on, let me look it up.
After this beat, I'm going to give it to David Swedlow, who seemed to be tracking this conversation before it happened in the chat. If you have anything more to add.
Oh, excellent. Alexander, you can
ask
you
a
can
question.
You can reach Alexander, you can reach me in private, you know how.
So actually, Nicholas was saying something similar. So one of the questions is Donald Hoffman's idea in the case against reality, the notion that space-time is really just a data structure and that we don't really perceive reality as it is. But there's something in that, if I think about it correctly, then something like negentropy is possible due to a living thing doing a super task. Effectively, the infinitesimal is something that is, we experience it, even though it's not alive in space-time. It's not alive in the projection that we have of reality, but it is alive in some real way. And so something like tracking Maxwell's demon as the notion of that's impossible. Entropy prohibits that if the demon is controlling an outside door because of something like that. But if the door is internal to the demon and it's basically the cell membrane, then the demon may be alive and doing a super task that actually allows for something like the distinction between a could and a should. Like there's some gap there that I can create that almost creates the reversal of time window that you're thinking of, that I can project forward and backward a little bit, a gap there enough to kind of effectively reverse time and do something negentropic.
It's from a construct standpoint, yes. I'm going to introduce a cheap hack, and I apologize. This is the hack against Rene Descartes about his concept of the homunculus. So if we treat Maxwell's demon as a quantum homunculus who is making decisions in these types of spaces, then at some point we can make that argument recursive. You can say there's a homunculus for the homunculus, all the way down until we still haven't resolved Zeno's paradox. We've just changed what our infinitesimal is. So we keep, if there's a decision-making process, then there's a homunculus. I mean, that's basically my counter to that. And what we're doing is admittedly, there is possibly a good takeaway here. We would be reframing our infinitesimal to a decision as opposed to a concept of space. So that would be a benefit, I think. Putting our infinitesimal of time instead of as a hyper surface of the present, breaking it down to a different structure might be beneficial. And I've seen some clever stuff talking about that exact process you're talking about. It's a transactional, damn it, what was it called? Transactional quantum, damn it, I forget the next phase. But it was, I can actually, you know what? Hold on, I have that. I have it. Transactional quantum. Oh, what is it? Damn it. Anyway, I'll get it to you later. The idea is that if the Maxwell's demon is there doing stuff and things are reversible, this particular theory was trying to describe the blending of the future and the now as a transactional process. So where it's going back and forth. So it's doing exactly that technique you were describing. So the amplitude comes in from one photon from the past, it then hits this future photon. And then what it will do is it'll negotiate like a handshake, like a TCP/IP packet. And it will say, hey, you want this quantity? And the other one says, sure, I'll take it. And all the other ones say, no, I don't want to take it. So that's the wave function collapsing. It then takes the quantity, and then the energy transfer happens. So there is a decision-making process being done in this theory of time collapsing. So what it's taking the infinitesimal and it's offloading it to the decision-making process instead. So that I have seen something that does what you're talking about, what we call Maxwell's demon. There is something that does back that up.
Nick, I'm gonna give you the last word. Is there anything more you want to add with your last comment?
Thank you, Daniel. So yeah, no, just on the same topic of Donald Hoffman's interface theory of perception, I'm actually not quite sure where this this talk of Maxwell's demon fits, and the possibility or impossibility of negentropy if we assume that consciousness gives rise to a user interface that is comprised of space-time. So that space-time is just a construct that allows us to be more adaptive from an evolutionary point of view. It's not really a question, it's more, I just want to throw that out there. I don't know if you're familiar with that theory of, and if you know that if there's an impact of infinitesimals on that.
Are you talking observer stuff?
Correct.
I see. Well, in that case, I go back to the same person who criticized Newton about infinitesimals. And this is actually fucking poetic. I'm going to read the bishop's actual words in his criticism of Newton. It's, it's in the form of a limerick. There was a young man who said God must find it exceedingly odd to think that the tree should continue to be when there's no one about in the quad. The reply, dear sir, your astonishment's odd. I am always about in the quad. And that's why the tree will continue to be sincerely observed by God. So it's very similar. We've gone full circle to exactly what the criticism of Newton was, and you did it. You did it. We went full circle.
What a great aesthetic ending. Thank you so much, Pat, and thank you everybody who joined in for that ride. I'm going to hand it over to Peter to plug some events right before we close out.
Yeah, thank you, Daniel. And thank you, Pat. Everyone's favorite genius bad boy is going to be here at 5, or Fridays at 8:30 p.m. And maybe you should just do a poetry night, Pat, next time. Just read poetry for the whole hour. Give a little spin to the dark Stoa. So just to plug a couple events, there's a bunch on the website. You go to stoa.ca. It's on the chat. One I'd like everyone to consider is the Mediation Campfire with Jason Snyder and Jared James and myself. That's every Sunday at 3 p.m. Eastern time. And we talk about mimetic mediation, how to mediate the culture war. It's been very, very interesting, or the liminal war that we're calling it now. And Nick, you have an event, it's not posted on the website, about tentatively called Coinage Game. Maybe you can talk about that briefly.
Put me on the spot. Can you guys all hear me?
Yep.
Right, so something I was going to present to Peter more in full on the weekend. It's essentially this idea of unfolding a concept in a hyperspace of all possible versions of that concept. So running it through functors, or this kind of transmuting boxes, to turn a concept into any version of that concept that might be more useful to us to grow our toolkit of concepts with which to make sense of the world. So basically the alchemical art of concept creation. If that sounds interesting to you, then join me possibly next Wednesday, where I hopefully won't make a fool out of myself.
That sounds awesome, Nick. I look forward to that. All right, everyone, just one final note. The Stoa is a gift, and this is Pat's gift to you. This is our gift to you. And if you feel called to give a gift in return, you can go to the link in the chat, and any sort of gift you feel to offer in return to the Stoa, there's an opportunity to accept it there. So thanks again, everybody, for joining, and we'll see you next time.